My name is Josh Foster. I'm based at King's College London. Some of the work that I'm going to present to you today was from a European Union project called Heat Shield. The broad aim of that project, it lasted over 5 years. It was a very large, multinational, interdisciplinary project aimed at increasing the resilience of the European workforce to extreme heat. Even covering some of the main points and key takeaways from that project in an hour would be very challenging, let alone in 15 minutes. So I'm going to focus on some of the lab-based experiments that we did looking at improving our models of economic loss with heat stress due to decreases in labour output. Heat stress significantly damages the economy. These effects are non-linear and highly related to the region that we're interested in. Work from Marshall Burke looked at whole countrywide percentage change in GDP per capita. And the data that you're seeing here is in a hopefully now unrealistic scenario, RCP 8.5, which would total up to around warming of around 4 degrees Celsius. Effectively showing that the countries closest to the equator, the countries that are already hot, suffer the most. So we see very large increases in global economic inequality. However, I would certainly argue that in regions like Europe, under these scenarios, I'm highly skeptical that there wouldn't be large economic damage. And I'm going to show you some data as to why I think that is. There's reasons why economists do this. They're very simple metrics, I guess, to analyze, but we can all agree that this is a very, very blunt instrument that doesn't really take into account lots of the areas that may be impacted by climate change, not least human labour productivity. Solomon Shang at Stanford University in 2017 looked at this in slightly more detail to try and partition out some of the areas which are likely to be impacted by climate change, which would then result in a loss in economic output. These include factors such as coastal damage, increases in violent crime, hospital costs, increased AC usage, and things like this. They categorized high-risk labor as those where jobs are generally exposed to heat, so agriculture, construction, jobs where individuals are exposed to high heat stress levels, so normally outdoors under solar radiation. Again, what's fascinating about this data is that this is based at the end of the century, RCP 8.5, and we're only seeing a reduction in the most extreme cases, high-risk labour, of 3%. What worries me is that people would look at this and think that labour supply, the human resilience to heat stress, is extremely resilient, so we don't really need to do much about it. And this is where physiology comes in, and it's so important. We need to be very, very careful when we're modelling impacts of climate change and heat on humans. We need to be very careful about the underlying mathematical functions that we use to form those projections. I'm going to talk about, there's many, I'm going to talk about a couple of very pertinent examples. From the data that I just presented, they used this function. This function is put together from the US Bureau of Labor Statistics. This is from a survey called the American Time Use Survey. Individuals, many thousands of individuals, so it's a very large data set, have a couple of questions on there about how they spend their time. One of those questions is the amount of time they spend working. So that then coupled up with climate data, meteorological data, can then be used to say, once we exceed around 25 degrees Celsius, this is how many minutes per day we lose in labour. Okay, that's one way of looking at it, but it says absolutely nothing about what happens during work. One of the other limitations of this is only using maximum daily temperature and not an integrated heat stress assessment metric, like some of the examples like Larry mentioned, WBGT, UTCI, and others are available. John Dunn in Nature Climate Change published a slightly different model, this time an improvement using the WBGT. Oh, here we go. Oh, you have to press it 5 times. So effectively what this is, when you look at the ACGIH guidelines, they're an American organization aimed at protecting American workers. There are work-rest tables which are aimed to advise workers and managers about safe work-rest ratios to prevent hazardous rises in core body temperature. So for instance, as the heat stress increases, per hour, a greater percentage of that work is required to be resting, again, to prevent excessive rises in core temperature. The underlying data for this is extremely difficult to find, and it was never intended to be used as a measure of human performance. So what we see at WBGT levels at 26 and above, this is about the equivalent of 26 degrees with 100% humidity, so already quite warm conditions. We see a dramatic fall to 0 when WBGT hits around 33 Celsius. These conditions are not uncommon, and we all know that people will be able to continue working to some degree in these conditions. So there's problems with the underlying functions. And this is where our physiological studies came in. We wanted to try and improve some of these functions based on empirical data. We had a fantastic team of researchers on this particular work package, led by George Havenith, but also advised by Simon Hodder, James Smallcombe, who's presenting to you later today, Ollie J, Andreas Flores, and Lars Nybo. The work was conducted at the Environmental Ergonomics Research Centre, where they have some of the best environmental chambers in the world. Some of the things that we can do in physiology in general is where we can recreate any number of thermally hazardous environments, whether that's extreme cold or extreme heat. We've already seen some of the incredibly high-impact work that Larry's done, looking at the extreme ends of human adaptability and some of the factors that change that. Many people in this room, Rob Mead, James, Larry, have used this to conduct heat wave simulations where we can expose older, vulnerable adults to 9-hour heat waves in some cases, looking at who's vulnerable and what cooling solutions might work to reduce the burden on air conditioning. In this case, we used it to look at the reduction in labor output. What we can do with these climate chambers is we have precise, if they're working properly, precise regulation of the air temperature, humidity, wind speed, and in some cases, solar radiation. This allows us to produce very high fidelity and highly granular information related to the climate on how that impacts human beings. This was a snapshot of one of our experiments. We had to develop a protocol which was generalizable, which was generalizable across a number of different industries, but also helps with some of the practicalities as well. So we used a treadmill-based protocol. This is an individual exposed to solar radiation at 40 degrees Celsius. And one of the tasks that we had to kind of overcome was to develop a simulation in the lab of self-pacing behaviors. Very briefly, we kept the cardiovascular stress relatively constant, and that's what we see in the field if individuals are allowed to self-pace. When people work in progressively hotter climates, the cardiovascular stress is relatively maintained, even up to extreme heat levels, but what changes is the metabolic output to allow for that. So there's a certain level of cardiovascular strain which workers deem acceptable, but in order to maintain that cardiovascular stress in hot climates, the work rate must come down. So obviously this has an impact on economic output. Happy to answer more questions about that later without going into too much detail. We measured work output at a fixed cardiovascular stress in an ideal environment, so 15 degrees Celsius WBGT. And then we measure, as we go to progressively hotter conditions, the change in work output. So each of these dots is going to represent the average response of a group of workers. And that's a heterogeneous sample which also allowed us to pull out the effects of body characteristics and individual fitness levels. So after many years, James Smallcombe and I spent all of our time in the lab for about 4 years doing this. We would then generate enough data to form new functions. So we formed sigmoidal functions based on this data. And again, we conducted over 1,000 lab experiments, ranging from 1-hour simulations, but also full-day experiments, which James Smallcombe led. And crucially, our models are adjustable based on a series of environmental factors, like I mentioned previously, and individual differences. One of our key outputs, which presents a significant improvement from previous models, is our ability to estimate labor capacity against a number of heat stress assessment metrics. And also, what's very interesting, in the 2022 heat wave in the UK, we saw conditions such as this: 40 Celsius, around 20% humidity. Already, labor supply is around 75% of the best case scenario value. We're also able to look at some of the changes in the very complex interactions with solar radiation using solar radiation lamps. See labor capacity again on the y-axis, air temperature on the x-axis. The black is in the shaded condition with low humidity here, high humidity, and then with higher clothing coverage, low humidity, high humidity. You can see that broadly speaking, solar radiation, of course, reduces physical work output and is something that must be modeled in the climate change and economic literature. Effectively, for around 20 different air temperature and humidity combinations, we looked at how physical work capacity and the physiology changes, again with solar radiation previously, but also with high and low wind speeds to try and develop an idea of to try and provide evidence of a non-air conditioning based solution. So relative humidity is on the y-axis. Air temperature is on the x-axis. We used the dual approach of a biophysical model validated by our series of empirical data, which is each of these black boxes. This is extremely useful and novel data in the sense that it provides a very clear overview of what conditions, electric fans, for instance, will improve work capacity, and if the workload was fixed, would probably improve thermoregulation. The green shows conditions where electric fans were beneficial. They improve work capacity by over 10%. And very interestingly, in very hot, dry climates, so over around the high 30s, around 37 degrees Celsius, evaporative heat loss is already high in these situations. The air temperature is higher than the skin, so it's going to push heat onto the body with having no additional beneficial effect on temperature regulation. So there are certainly some very hot conditions where we need to rethink how we keep workers safe and cool. And finally, we conducted, James very much led this study, modifying our models based on 1-hour work versus full-day work. And we can see that in the dotted line, the drop-off in productivity against WBGT significantly grows once you get to a WBGT of around 28. Thankfully now, we published this in 2021, and we have many use cases of this model being used in the economic and climate change literature. This is one example by Luke Parsons, who compared a previous model with some of those kind of problematic assumptions, I guess, that I mentioned in the start of this presentation, compared with our new model. And perhaps the best way of looking at this is heavy labor lost, hours per person per year, with the old model against latitude, compared with the new model. This is not projection data. This is from 2017. This is real climate data and not a fictitious scenario if things continue to go badly. This physiology work isn't perfect. We completely acknowledge that it almost entirely ignores certain adaptation measures and things like this. But I think it's just a really quite alarming way of looking at human capabilities in the heat and the impact that can have on the economy. The key take-home message is that physiology can play a critical role in unexpected areas, in this case, economic modeling of climate change. In addition to that, though, we can use physiological studies to directly evaluate the effectiveness of low-cost sustainable solutions. We showed that electric trams were very harmful, but can also be extremely beneficial in hazardous heat environments. The Heat Shield project covered a wide range of sectors. It covered, including but not limited to, agriculture, construction, manufacturing, tourism, and transport. And within that, we developed a series of validated solutions within each of those sectors, based again on physiology studies and field experiments within each of those sectors. We published these manuscripts as a series in the International Journal of Biometeorology, and it's been really, really encouraging to see how often our models effectively have been taken up by the climate change and economic literature. Thank you.